Okay, my goal of this video is to conceptually understand how a simple filter in OpenCV works. Because OpenCV is so awesome, we can just blur an image in one line, but I don't like taking things for granted. So I'm going to try to implement this Gaussian blur without actually calling this OpenCV function. Let's take a couple steps back and first understand Gaussian blurring. I'm in the OpenCV docs again, and I see that in this method, a Gaussian kernel is used. So we take in the image, and we also take in the width and the height of the kernel. But what is a kernel? I'm assuming that it is also a 2D matrix because of its parameters here, the width and height. But we are provided a get Gaussian kernel function. So let's use this function to mess around, print some stuff, and see what the kernel really is. I'm back in the code, and here I have a simple script where I read a frog image, and I apply the OpenCV Gaussian blur function, and just a little bit of code to display the window so I can actually see the result of this blur. So let me just call this file really quick. On the left, I have my original image. On the right is the blurred image. So let me just get that out of the way for now. And use this new get Gaussian kernel function to see what happens. Okay. It's going to be a 5 by 5. Interesting. We get a 1D array. But I'm just going to multiply it by its transpose so we can get the full 2D array. Okay, there we go. We have our 2D kernel. So we're getting somewhere. We can see what the kernel looks like. But how does this actually apply to our filter? We don't know how yet, but let's figure it out. I found this great post on how to use kernels on images. Let's take a look. So we have our kernel here, which we just described a few seconds ago. And we apply it to an image of dimensions w and h. So let's see. Assume that the center of the kernel is positioned over a specific pixel in an image, and we multiply the value of each element in the kernel with the corresponding pixel element. So we take this one here, apply it here, take the next one, apply it here, and so on. But because we will normalize our kernel, which we'll see later, that sum will already represent the correct weighted average. We won't have to take the average value in this case. And then we can replace this sum on the pixel we just defined here. Okay, let's implement this in our code and just do it for one pixel. Okay, so on the right side here, I have an example of a Gaussian kernel. This is the mathematical formula that generalizes it, but we don't need to get into detail here. I just want to notice a couple patterns I see here for this 3 by 3. First of all, I notice that the weight of the middle pixel is greater and kind of spreads out lightly towards the ends of the kernel to kind of blur out the surrounding pixels. And there's also this scale factor here. If I apply this scale to every element and sum up all the elements, I get 1. And the reason we want a sum of 1 for a Gaussian kernel is so that we don't change the brightness of our resulting image. Okay, so here we have our 3 by 3. This blurs it slightly, but I want to blur my image a little bit more, so I expanded this kernel into a 5 by 5, applying the same pattern. It's very centralized with a heavy weight in the middle and spreads out lightly towards the ends. If I sum up all these elements, I get 273, so my constant will divide this matrix by 273, so I have it normalized. So let me print this kernel and compare it to the get Gaussian kernel function. As we can see, this matrix is similar to the one in our previous script using the built-in get Gaussian kernel function. So let's work with our matrix we developed here and apply it to every pixel in our frog image. I want to use this image for reference. So here our example is a 3 by 3 kernel, but I actually want to use a 5 by 5. And in this case, we will assume that our current frog pixel is xy, and we will be looping over the kernel from -2 to 2. Why? Because we will assume that the center of our kernel is 0, 0, and for 5 by 5 it will be -2, -1, 0, 1, 2. So applying the drawing to this figure, let's implement that loop. Okay, so our current pixel from the frog would be x plus kx, y plus ky. And then we need to get the weight from the kernel, which would be kx plus 2, ky plus 2. Okay, and now we need to multiply the value of each element in the kernel with the corresponding pixel element. Okay, and now we want our output image, or the blurred image, to be this new total value. So let's call our output image output, and we'll set x and y to be that total. Now we can loop over every pixel in the frog image so that we can apply the kernel to every pixel. So let's define our total at the top to be 0. Okay, and this will be the current iteration for one pixel. So now we need to basically do another nested for loop to go over every pixel in the frog image. So we'll go over x. For x in range 2 to height minus 2. And for y in range 2 to width minus 2. Okay, and since we're changing our output matrix to set it equal to total, let's just define our output matrix at the beginning as just zeros. Now I just want to clamp all pixel values into a valid image range from 0 to 255, and then convert the array back to 8-bit integers. Okay, now let's uncomment this out so we can view the windows and see if this works. And there we go. We were able to do the Gaussian blur manually without using the built-in OpenCV function. And there's one thing I want to highlight here. Notice how the border here is black. The reason behind this is because since we were applying the kernel to every pixel, the overlay would not allow the kernel to be in a position such like this. So we had to apply the pixels to basically the inner part of our frog image. You can see the output here being a 3x3 without the borders included, and that's what's happening here. Since we initialized our output array to be zeros, that corresponds to black, and so those pixels weren't changed in these nested for loops. This is why we looped over x in 2 to height minus 2 and y in 2 to width minus 2, so we can remove the borders. So to wrap it all up, a blur filter in OpenCV works by replacing each pixel with an average of the pixels around it, and this is defined by a kernel. Gaussian blur does this smoothly by giving more weight to nearby pixels, which reduces noise without changing the overall brightness.